So what is design flood? A design flood is a hypothetical flood, which can be either a peak discharge, a hydrograph, a runoff volume, or a flow level, which is adopted as the basis in engineering design of project components. You may be required, for example, to find a design flood to be adopted in the design of a spillway of a dam. Okay, so we need to find the dimensions of the spillway. You need that design flood, a specific design flood. You may need a design flood to design a detention basin, okay, or any other drainage works. So to provide safety to downstream areas against flooding. You may need a design flood to design the entire urban drainage system, to provide safety in urban areas such as walkways, roads, and residential areas. So a design flood is a flood with a certain probability of occurrence, below which our structures, by structure I mean bridges, dams, roads, pipes, can function normally with a low possibility of failing. Okay, so it's a design flood that guarantees a certain level of safety. Okay, and flood levels above the design flood may incur some sort of failure. Okay, some examples of system failure can be seen in these images. For example, we had floods recorded in January 2020 on the Gold Coast, when more than 300 millimeters of rain fell in one day, causing dangerous flooding and severe damages. For example, this dam here, which failed after a strong rainfall event. The selection of the design flood takes into account economic factors, the severity of consequences if that structure fails, and the community acceptability if a structure fails. We have here 3 examples. The first one is a urban drainage system that can handle a very large amount of rain. So that guarantees the maximum level of safety, of well-being for the residents of that area. Okay, so it's an acceptable level. However, it may be too expensive. The second example is an unacceptable design because it's too small to cope with a large rainfall event that will cause lots of damages, including flooding, inundation of houses, traffic congestion, and other things. The third example is acceptable, but people don't want to see that situation very often. But that may be the optimum design because it's not too expensive, and still people will be okay with the situation in case that system is not able to cope with this design with a certain large and extreme rainfall amount. We have here another example that like of a road or a drainage system design, which may be acceptable in some communities, but we don't want to go through that situation very often, okay? So there is like an optimum value for a design flood to be used in the design of the various systems that are part of the entire drainage network. And as I said before, using the highest rare flood could be uneconomical. This will incur large investment for infrequent flood occurrences. Urban drainage systems, they are made of minor drainage components and major drainage components, okay? The minor drainage system components, they are usually used to contain or to convey the small flows in our urban areas. These pipelines prevent stormwater damage to properties and also limit the frequency and quantity of surface water to a level acceptable to the community. They are usually designed to cater for flows with a 5-year average recurrence interval. And here by 5-year average recurrence interval, I mean a rainfall event that is expected to occur once every 5 years. The pipelines don't always follow the natural drainage path and are usually aligned along property boundaries and the roadway curb and channels. They are used to cope with a low rainfall amount because we use a very low recurrence interval for those systems, which is like a frequent flood, a frequent rainfall event. Once every 5 years, that's frequent in terms of urban drainage design. The major drainage system caters for runoff from storms producing higher peak flows than the minor drainage system has been designed for. The major drainage systems, they are designed to handle flows resulting from storms with 100 years ARI or above. So a flood or a rainfall event that is expected to occur once every 100 years. So that's a very rare rainfall event. Therefore, these systems, they are more important than the minor drainage systems because they are used to convey the big amount of floods. A roadway, a drainage channel, a pipeline, or a combination of the above may act as the overland flow path. As a general rule, the finished surface level of the allotments adjacent to the overland flow path must be at least 30 centimeters above the 100-year ARI flood level. Okay, now since measurements of flow or runoff are rarely available in catchments, the estimation of design floods rely on models, mathematical models, that transform design rainfalls into design floods. Okay, so it's much more common to have rainfall records than flood records. Okay, so we rely on rainfall records to derive a design flood for a particular area. Okay, so design rainfalls, they will be the input in our models. Okay, and by model I mean a mathematical model that represents the transformation of rainfall into runoff in a given catchment, or the response of the catchment to a rainfall amount or to a rainfall event. And design rainfall data is readily available. Okay, so that's the advantage of using design rainfall data instead of river discharge or flood data, which is rarely available. Okay, so basically we have a hyetogram. A hyetogram is a graph that shows the distribution of a rainfall event over a period of time. So this is our catchment, which has its well-defined boundaries, and in hydrology and in all like a urban drainage system design, you will always be working with catchment boundaries. Okay, so you have to have like a well-defined area, including the entire area that drains into a single point. That single point to which the entire area drains is called the outlet of the catchment. At the outlet of the catchment, we have the hydrograph, which represents the response of the catchment to that particular rainfall event. Catchments will have different hydrographs depending on their characteristics. For example, the slope, the length of the main river, the shape of the catchment, the size of the catchment, all those things, and the land use, the land cover of the catchment as well. All those things will make catchments respond differently to a given rainfall event. Okay, so we know this, we know the hyetogram. We also know the characteristics of the catchment. So we can have the hydrograph, we can have the peak discharge, we can have the volume of runoff, which is the area under the curve of the hydrograph. So we have all the flood, the design flood components that we need for our design. Okay, so in this course, the first weeks, we'll be looking at ways to transform a rainfall event into this. Okay, so this is what we want. This is what we need in order to design our structure. That could be a bridge, a culvert, a drainage system, or a spillway.